Morning, guys.
Morning, Alan.
All right. Morning, Z.
Good morning, Alan. Good morning, everyone.
Good morning, George. Is this your first time here?
It's not my first time. I just try to join when I'm don't have another meeting.
Okey-dokey. Welcome in. See you there. Morning, Michael.
Morning, Alan. Hi, everybody.
Yeah. We can give it a couple more minutes. Morning, Howard.
Morning, everyone.
Good morning.
Good morning, Oliver, Olivier, sorry. Right, just got a little bit diverted there. Morning, Bobby. Let's get going. Olivier.
Good morning.
Video. Okay, I can share my screen. Sure. Okay, hopefully you can see my attendees there. Okay, so I've got a couple of topics here that maybe we won't be able to cover all of them, but I've got a few things going on here. Let me I just want to get the list of attendees up. All right, so there's a couple of things sort of still dragging on here, and my apologies on this. I've just been going around the houses, and I guess I'm slowly learning, guys. So thank you for your patience. So what I wanted to do was discuss the gauge of cables. So I guess what I've learned is that PCI SIG is actually specified 30 gauge as the standard. Is that fair to say?
Alan, I think they didn't say explicitly, but they do imply that.
Right. I guess I've seen it everywhere. So, and you've been emphasizing it multiple times. So
Yeah, just not on the spec. So not on the numbers, not on their spec. So yeah.
right, okay. So I've got some I was also looking at near stack. So I wanted to discuss, this was just from a size perspective and a height profile perspective. So this is just sort of comparisons. And there's nobody on from Molex, but they did give me some data that sort of helped me ascertain. Wait a minute, where is it? Helped me ascertain the actual difference between the two. They did do a nice comparison for me. And for some reason, I've got too many of there it is. So they've got their near stack, what they call HD, which is a 34 gauge, and their PCI near stacks are 30 gauge, just like everybody else. And I was investigating this from a height profile perspective. Is you've got the lower profile ones, so I'll show you a bit of that in a moment. But I guess they're showing these tables here. This is a 2 meter length cable, and it 34 gauge, and it's a 23 dB nominal loss, or 25 max between the fifth. Well, it's 17.5 gigs. It's 25 dB, 27. Whereas the 30 gauge is in the region of 18. Or as I put it up here, you're at 7 dBs per meter versus 13 dBs per meter for the 34 gauge. First of all, guys, unfortunately, the IBM, sorry, the Molex guys aren't on, I don't believe. By the way, morning, Mitch. In general, when these on these specifications, guys, is this from the mated connector, the pad on the PCB, to the mated connector on the other end, or is it just the cable connector, or is it just the cable itself? These sorts of numbers. The Z, or I mean, when you report a cable.
Yeah, I think I cannot speak for Molex data.
No,
So
no. Well, I guess as an industry, if I said what is the loss of your cable and you said it was this much, would you just be given the cable itself, the connectors that are attached to the cable, or from the PCB pad to the PCB pad? What would you do for Amphenol, and what would Lopes do? Is there an industry practice when you quote a cable loss?
yeah, so usually the more specific wording for the cable itself, right? It's we call the raw cable loss, right? And if we do the whole thing, we call the cable assembly, or even more specific, the mated cable assembly.
Is there a another chart on there that shows the assembly, including the connector? Or is it just the cable?
I guess this one probably just looks a bit like the cable itself, but yeah.
Yeah, I don't think it's tied to a particular product. It's just
No,
like
no, this looks like a generic. So yeah.
figure out your budget.
So actually, it's going to be worse than when you add the connectors, obviously.
Yeah, connectors can be a little noisy.
So that means the bulk cable, this one.
It could be the raw cable Z. The loss value presented here could be the raw cable itself.
Yeah, possible, yeah. So
Right. Okay. All right. Well, basically, we're saying we're in this just for the cable. If we assume just for the cable itself, then we're in the zone of 16 dBs for a meter. And I guess the overall budget for a PCI channel is in the region of 30 to 40 dBs for PCI Gen 6. Does anybody know what the overall budget is?
you mean the PCIe spec,
Yeah.
the spec?
Yeah.
Yeah, the spec is 32 dB.
So we got a 32 dB total channel loss. And we've got 16 dBs. We got 16 dBs in the cable. Right, so
Where you get to the 16 dB? I tried to.
well, there was just that standard cable there. For one meter is like 16 dBs per meter for the 34 gauge.
Okay, 34 gauge. Okay, so yeah, so Yeah, the number I think what you just showed is 13 dB per meter, right? And connector maybe like 1 dB.
Oh, 13, yeah, sorry, you're right. I was sorry about my bad. I was 16 gig. Okay.
Okay. Okay,
13
yeah,
dB.
I try to figure out where the 16 number come
Yeah,
from.
13, my bad. So it's 13 dB per meter versus 7 dB per meter, right? So for round numbers.
Okay.
Yeah, so we're twice as bad with this cable. And obviously in the channel you need to allow for escaping the die, the package, the PCB through the connector. So assuming that's just raw cable, we've got 32 minus 13, we've got 19 left then, right? So we got 19 dB, divide that for each end, 2 nines are 18. So we got 9.5 dB per end to get out of the package on the PCB and through the connector to the cable. So I guess if I flash up my model, sorry. If I flash up my model here, we are, so basically we've got a channel from the die, which is going to be somewhere around here, worst case to the here. I think I had about a 2-inch total from the die bump, but obviously it's got to traverse these impedance discontinuities through the connector to the cable. So we've got a total of 2 inches from the die bump through the ball of the package. And I must admit, these are probably these big chips, so they'd be like CoWoS, so they have some sort of passive interposer, which I guess won't help things. So effectively we've got 9.5 dBs to get to the cable at both ends. So what I'm trying to get to the point of is between these modules, you're going to have a 1 meter cable, absolutely worst case, between these modules, and it's probably going to be more in the region of closer to 0.5 meter. But if we use the 1 meter as a worst case, so we've got the full. So it doesn't seem unreasonable. I remember when we were doing OAM modules, albeit that was at PCI Gen 5 speeds, not 6. Although, so guys, on the Gen 5 versus Gen 6 is PAM4. It's going from NRZ to PAM4. So you're still at the same Nyquist frequency, right? So does that impact the loss, I guess, or you're more in the noise because of the PAM4 encoding, I presume?
Yeah, so that mode changes only impact the noise. Yeah, that's correct. But I think the calculation you just mentioned, I think, did you put the root complex side and the adding car side on non-root complex side package loss?
Right. So, well, in this sense, these devices are talking to each other. So these connect between each other. As PCI link. So therefore, the loss on one will be identical to the loss on the other. It's like going between two OAM modules.
Okay. So what's their package loss?
Well, I don't know. I mean, so I guess there's the industry nominal. So in like the OAM module, for instance, on the OAM module, you had to go, they had an 8 dB loss going from the die bump through the package, through the OAM PCB to the mirror MES connector, and through the mirror MES connector to the actual PCB pad on the motherboard, i.e. it was a mated mirror MES connector. I remember that was a budget of 8 dB. And then you had 8 dBs both ends, so 16 dB, and I think it was a 30 dB total we were working to on PCI Gen 5. So that left us with 28616, 14 dB for the UBB motherboard. That was the way the calculation was done back then when I was working on that.
Yeah, that actually is a similar number as root complex package, right? So I think the spec says 8 dB. So yeah, that I think match. So 8 dB from chip to PCB surface, right?
And then the end point, I guess, what budget do they give for that in Genesis?
8.5 for the adding card, but you are talking about the kind of the same chip, so maybe yeah. That save you half dB there.
So they're saying 8.5 for the endpoint and 8 for the root complex. Is that what they're saying?
Yes, yeah.
They're so close. Why don't they call them the same? Okay. And then they're saying it looks like if they're saying a maximum internal cable is 1 meter, and we've got to use 30 gauge, which is like in the order of 7 dB, then we got 16 plus 7 is 20. So we got 23 dB as the channel design, even though the budget's 32 dB.
Yeah, so in that spec, for the internal cable, right, copper link cable,
Right.
they specify 7.5 dB, include the two connectors and the cable, right? Everything.
Oh, so 7.5 dB includes the connectors.
Yes.
And that's 1 meter.
Yeah, that's for 1 meter internal cable, yeah.
Does it include both connectors, the mated connector down to the pad on the motherboard?
Yeah, that's correct. Yeah.
So mated connectors. Okay. Well, that's pretty impressive then. So well, again, back to my point though, then they're giving you 7.5 dB plus 8.5 plus 8 is basically 3/8 is a total of they're given a total of 24 dB budget for a channel that's capable of 32 dB. Is that right?
Yeah, I think I agree with your calculation. Yeah.
Okay. So is there a reason why they specify a channel capability and then actually only use up, you know, why are they saying do that? Why not say if they said you're allowed to use for whatever cable you want, as long as you're within the 32 dB budget, then technically speaking, if we've used 16.5 out of 32, we've got 15.5 left for the cable, whatever cable we want to use. I guess I'm trying to understand if I'm missing something technically that means it won't work. You have to use a 24 dB loss to work in a 32 dB channel.
So I think the PCB routing and the VIA, right? Those are the left four.
Oh, so you're saying that 8.5 dB is just for the package?
Yeah, 8.5 only for the package from the
right,
chip to the PCB surface. Yeah.
Okay, so from the package to the PCB, then you've got the PCB trace itself. So the rest of the other 8 dB is for the traces in the vias. I got you. So basically what you're saying then is you've got, if we've used up 24 dB for the cable and the two packages, we've got 8 dB left for the PCB traces.
Yeah, for routings. Yeah.
So, or 4 dB at each end.
Actually, it's actually okay. In their spec, my understanding is since their topology is from the root complex to the add-in card, right? So I think the 8.5 for add-in card include the routing distance or PCB trace on the add-in card.
Okay, so that means we're back to a total of 24 then.
Yeah, if we for your case, if it was the same, yeah, it's yeah.
So I guess it gets back to my question then is you've got a 32 dB channel that are only letting you use 24 dB of.
So the 2 dB channel, you already use the 24, right? For two package and the cable connect, right? So you have 8 dB for routing.
All right, so sorry, I thought you were saying that it included the routing on the endpoint.
Yeah, endpoints is already done, but from root complex to the cable connector, right? They are routing. All the basically is in your screen, basically this one, right? Oh, yes. Sorry, okay. So yeah, you are right. Because you are symmetrical, the other side is symmetrical. You basically want their budget divided by 2. Okay, yeah, I guess now, yeah.
Yeah, so I'm guessing if we've got 8 dB to get out of the package and across, this is less basically from the package ball. I mean, from the die bump to the package ball is going to be, call it an inch for round numbers. And then from the package ball to the connector, worst case, I'd call it an inch. So I'm assuming based on OAM was 8 dB that, that could be 8 dB. We could, and by the way, that was through the connector to the motherboard. Now we don't have a motherboard, we just go straight to the cable. So we're in a much better situation than OAM was. So in my mind, if I give 8 dB to get from the package to the pad of this connector, and then we have of the order of 13 dB plus the connectors, we'll call it 16 dB for the 34 gauge cable, and then 8 at the other end, that's my 32 dB budget. So 34 gauge cables, perfectly fine.
Yeah, I think you are in a better situation than the original PCIe committee decided the things, because like Zheng said, it's considered as an add-in card, right? So they have to leave enough budget for the add-in card to route on the add-in card PCB, and that's why they give the add-in card significant amount of budget to route. And if you in your situation you don't have that, especially your chip to the cable has much less the packaging or the socket loss compared with the CPU have the socket to the motherboard, then yes, you got a significant more budget for the routing cable.
Right. So is it fair then? Thanks, Bobby. Is it fair then for me to say, because you guys make these connectors with 34 gauge cable, right? Z? I'm Lopes.
Yeah.
Right.
Yeah,
So,
so we have no issue to make the cable, right, for what you need. The only thing, yeah, you need to figure out the insertion loss budget and the noise you are going to handle. Yeah.
so I guess the big missing question on this is the noise. So is there a worse noise situation with a 34 gauge versus 30 gauge? Does the noise or
Should not be, I
should not?
think. Yeah.
Sorry, Izzy. Say that again.
Yeah, it should not be worse than the 30 gauge. That's what I think. I think Ariel also always say the same thing.
Okay, and you might have modified the connector design slightly on PCI Gen 6, but we can use the PCI Gen 6 connector, I'm assuming if you've made any mods compared to the Gen 5 one.
Yeah, we use the connect, yeah, and the pedal car may be modified a little bit, but I think that basically is, yeah, still the same.
All right, excellent. So I'm going to conclude that we can use 34 gauge cable. Sorry, and by the way, I mean potentially we could go to 32 as well, I guess, you know, and it'll be because, you know, by the way, let me just, I mean, obviously, thank you to Lotz and thanks to Z sent a cable where we did some measurements. My son actually has the Amphenol's cable where he did measure it. It was only 1 millimeter. So I'm not sure if you sent my son a 34 gauge cable actually, but anyway, Lotz sent me a 30 gauge cable, which if I just put my camera on, there we go. So oh no, you can. So this is the 30 gauge cable, and it really is solid and chunky. and you know, Lotz were saying about the folding. I can see the challenge. We don't actually have to get them pre-folded probably at manufacture. And I know that this is significant compared to significantly bigger compared to 34 gauge for sure. So I guess in that sense, we've. Oh, hang on. I was showing that to myself, wasn't I? Did you see me sharing it or not?
Yeah, we did.
We feel we did.
Okay. So if we just zoom in here, by the way, this is let me just, this is a Lotz low profile one. Let me just turn off the Lotz low profile one a minute. Okay, so these are the Molex near stacks. So this is their PCI by 16 with 30 gauge cable in it. And by the way, it's actually a longer connector than the standard MCIO, which I was a little bit disappointed in. But they've actually done a pretty good job of representing the gauge cable, because you can see this is 30 gauge cable. And in their HD version, which I'm thinking of using for the point-to-point, because it was smaller and because of the height profile, that was where I was going. There's our 34 gauge cable, so you can see how much smaller the cable is. So it's nice to have a representation, a true representation in the model. So that you know, this was the other thing that I had. Whereas I think the other models that I've got basically just generalize the cables into one bulk lump and aren't necessarily representative of any particular gauge. So this can give us a lot more routing options. The other thing with these lower profile capability is if we did stay with the 13mm space we've done, we can actually fold cables and route them across the top as well between modules. So it gives us more routing of the cable between the modules. So this is a reason, you know, I'm trying to get super flexibility in terms of the ability to configure different topologies between these modules, and hence why I'm spending a bit of time on that. So what I was thinking was, so I was thinking that maybe we could keep the host connections. These by 16s connect to the host, so we could keep them at 30 gauge and route up to the host. But the ones that go between module to module, we could go to the 34 gauge. Was where my head was going. So just looking at the height, switching to height profile now. The near stack was quite attractive because I think it offers the lowest height profile of about 9.8 millimeters, less than 10. But you guys have both been sharing your, so let me just turn off the near stack stuff and put on the low profile one. So here's your low profile one, which I believe is, take it to the top of the tab, is 10.8. So it's an extra 1 millimeter. So it's a lot better than the original 14 millimeter that we were, or whatever it was we were dealing with on the standard MCIO. So this is really quite close. Plus, obviously, the MCIO is much more of the industry standard. So the only disadvantage, if I pop the near stack back on, is we actually, what happens is we lose. This one's longer than the standard MCIO, but these little ones are shorter because they have less IO on them, and we're looking at using less IO. So, but actually, in our universal topology interconnect as well, we're reducing these IO counts down. We don't need to use all of these, so we do actually lose a couple of pairs. So that makes things even better on these ones. Whereas the main host connection will be a full-blown MCIO with all of the sidebands for connecting to the host. So so I guess in conclusion, I'm saying I think I'm concluding then that we stick with MCIO. So let's just turn this off again. Let's turn off near stack. If I turn on the full MCIO implementation, which is what we've been working with, this is the standard ones. These are the Amphenol ones, but the standard height. If I put the standard height Amphenol ones on, you can see that at the moment, that's the highest point. We're at 14.8 millimeters, you know, so the near stack was a big win over that. But your new low profile ones, this is Lotus's version. If we turn that back cable back off, I think I just said that. I said that was 10.8, 10.9. So we've gone from 14.8 to 10.8. So I think that's a big win to keep the MCIO in play. As an industry standard, I think that's good. And I think we're saying we can do 18 gauge, 34 gauge for the 1 meter length between modules. So I think that's my final decision. Is there anything? Would you support that, guys? I guess Z, Howard, in terms of a viable way forward, is there, or does it make you nervous what I'm saying?
I don't believe so. 34 gauge is pretty thin. If we go to 32, that'd be nice. The low profile, I think, is our best bet in this application, and hopefully we'll see business from other places for as we're seeing a push for lower and lower height product. Z, do you have a comment?
Yeah, I agree. It's reasonable here. And 34 gauge is a thin wire, and maybe yeah, I probably need to check with engineer how um the on the reliability side, right? Whether it's easy to tear off, or basically during the operation what we need to pay attention. But I think generally I don't have issue with that. Yeah.
Okay.
Ariel, do you have a comment about 34 gauge?
Well, the size to begin with is really small. Soldering may be, termination may be
Yeah, it's
a
fragile.
challenge. It's fragile, yeah. Because the smallest that we have done so far in the assembly is 30. We haven't gone the assembly stage for 32, or even much more on the 34.
I think if and Alan, you can maybe relate to this, as the part is laser attached, welded, soldered, whatever. The wire that's attached, of course, is truly permanently attached.
Right.
And the very thin wire, you end up with a hinge at the point of solid as it moves away. So as that wire is bent, the position of the wire, or the point of bending, is right up against where it's solid.
Right.
So the thinner it is, um, the more fragile it is. And since it's copper, anytime it moves, it work hardens. And so as that, just like when you bend a paper clip, you bend it, and eventually it breaks at that point. And so that's just one of the considerations. So if we can, as a goal, move to 32. You bent those parts that are 30, you realize how stiff they are. And if we could go to something that's not 34, that would increase reliability by maybe not an order of magnitude, but a lot.
So I think I understand what you're saying. I guess that's so in the manufacture, you're going to obviously have to put the bend in here and solder to the paddle card. I guess that's what you're saying, right?
Yeah, and it's solidly attached.
And it's solidly attached. But then you've got this molding around the cable. So in operator use, you're going to bend it here, not at the solder joint, right?
Well, as you bend it, you've got it's like your arm in a sleeve. Um, as it's bent, the wires push and pull with each
Okay,
other.
so you don't get rid of the stress actually all the way inside that molded connector. I was
No.
thinking that the mold would keep the stress away from the joint.
Yeah. Well, as we talked about before, the sharper the bend, the more those wires squirm in that sleeve. And you want them to, but dealing with 34,
Okay.
you can imagine it's a very fine wire.
Right, right. Okay. I mean, again, these so this installation in terms of use is I guess I'm proposing this is a manufacturer at manufacturer installation. These aren't installations where you know an IT guy will go in and modify these on a frequent basis. So these are sort of insert once. And I guess that's the case on most servers, right? I mean,
Yeah, certainly. Most everything is made at once, hopefully never see it again. So it's
okay.
like, but in some cases you have an MG, in some cases you have a Toyota. And the nature of modifying things or moving things or changing things.
Okay, so from a Lotus perspective, you've always done 30 gauge. So I guess from Amphenol's perspective, I've seen 34 gauge on your websites. So you do 34 gauge in this MCIO already, correct? This isn't going to be a special for you.
Yeah, I will guess so, but I think it will be very low volume, or it's not certainly not as the popular as 30 gauge. Yeah.
Okay.
Yeah.
So I guess the conclusion there then is all right. So the conclusion is basically availability. This is another modification, and or so Amphenol do it, but probably only in low volume compared to the other stuff, and Lotus would have to tool up for it.
Well, there's lots of opportunity for yield problems.
Right.
The finer the wire goes and the closer they are together. And as we move forward, that's a balance that goes to price and cost and and yield. So got to be careful with those fine wires.
Okay, fair enough. So I feel like I'm getting pushback that this isn't a good idea.
Well, bigger wires are easier, is the comment. And if we have DB available to us, or ability to bend or whatever it is, we'd like to get all that we can. And so 34 gauge wire, if you if you have one in your hand, it's like, yeah, they're fragile.
Yes, I think on my side, let me check with our production team, right? And before really make this commitment. So
Okay, yeah, no, it's the if you can do that.
yeah.
I guess. Yeah. Like I swear that I definitely seen a 34 gauge MCIO cable on DigiKey or something like that, or on your website. So, but yeah, it would be good to get more clarification on that, because obviously we've got some tooling changes like the surface mount connectors, but I didn't really necessarily want to be going down the avenue of cables that don't exist. So so yeah, if Amphenol are already making them, then that keeps it in play as far as I'm concerned. So if you can get that, Z, that would be appreciated. Okay. All right. The other topic I wanted to switch to, is I'm going to need to stop sharing and I'm going to need to dial in from my other laptop because it'd take too long to load the model otherwise. So let me just see if I can quickly dial into today's call. Sure. All right. So hopefully now I'm going to share my screen. Okay, so if I what do we want to do here? Like that one. Set. Power connector. Wow. Okay, let me isolate that lot. That might take a while. But so I wanted to just touch on this exoskeleton and how it's been helpful looking at the power bus bar. So I wanted to talk about that. There we go. That was quicker than I expected. Good. Okay. All right, guys. So let me just turn off the insulators so we can get a view of the copper bar. There it is. And also just turn off that T-bar. So what so this is the actual current makeup of the concept. And these are the copper bars. We've basically got the middle bar is ground, and shouldn't select it. And the other two on the left and the right are the 48 volts. Now, obviously, the first observation that Howard made was that they're all the same size when the middle one's carrying twice the current of the other two. So yeah, it was just when we were throwing the concept together, that was what we did. So we can proportion these to a certain extent. I think we are somewhat restricted actually because of the and at the moment these are Molex 75 amp power pins, and so we're somewhat restricted by the size of these pins and the hole that they're required. So if we, in fact, let me just hide these are the actual pins that go in. I'll hide the pins. Being very slow, sorry. Let me just hide those. There we go. So you can see this the pin in the socket. So this is, we don't have a lot of room to make these bars any narrower. That's the challenge. So we potentially could make this one a bit wider. I can look into that. But anyway, so Howard did a basic sort of analysis of this, and came up with various. I guess I don't have the details to really flash up, but came up with various gauges of cable. You use 200 amps, right, Howard? We basically need of the order of 100 amps at 48 volts, and I think you overrated it to 200 amps, and we were looking at that, and when you look at the different types of cable you can buy with various gauges, they're rated at temperature rating, so current at a certain temperature. And I guess my question on that is that basically the bus bar, when you say it can do 200 amps at 60C or 75C, is that the temperature it will go to, or Can somebody explain that? Because I always think of IR drop is what I'm worried about. Is how much power am I losing in the bus bar? So can anyone explain the temperature relation of a copper cable that's rated at a certain current at a certain temperature?
Yeah, I think the way that rating works is given an environment of 65 C, which is very hot.
Right.
This you have wire in a tray. This is that the wire at that 65 C environment will not overheat. So
Okay.
you'll get some watts dissipated in the wire. And given a environment where you've got a bunch of these wires in a tray, you're not going to run away.
Okay. All right. Thank you, Howard. That makes sense. Okay. Okay, because I was looking at the relative resistance, and I'm looking at how many watts am I dropping compared to, what's the efficiency loss percentage wise. And so I think we did some cross-sectional area. Obviously, the concern we've got in the model here is actually that these holes obviously give you neck down points on the copper bar, but equally these pins are going to be soldered in. I'm assuming that we're going to solder them in rather than press fit them.
I don't know how those are attached to the bus bar.
I guess there might be variations on either solder or press fit. Is that possible?
That would be a very, very hard part to solder.
Right. Yeah, no, it would.
You'd have to run it
So
through.
you're assuming that would be a press fit then, are you?
I'm assuming it would be a press fit, yeah. Like there would be a ring of splines around that, or
Yeah,
something.
actually, I don't believe there are, to be honest.
The smooth.
I think they're smooth.
Yeah, I think I saw the model. They're smooth.
Yeah, no, they are.
Yeah.
So I think they're designed to be soldered. I mean, obviously, you'd need a very serious solder bath. You'd have to get everything, the entire copper bar up. But in these situations, I guess that might demand that, right? So,
Well, you'd also be heating the beryllium copper spring that's on the inside, and it would lose its, it would change its properties completely if you soldered it in place. So there's some real issues with how that is, and I just don't know enough about them.
okay, I'd have to.
Could be of any help.
This is standard stuff off of the Molex's website, so
Yeah.
I'd need to go back and I've not looked at it in that specific detail. But you said you do these type of pins as well, right?
Yes, well, I know Amphenol and Molex and Lotz does similar these.
And everything that you do is press fit, then, is it?
I don't know enough about it.
Okay. So obviously, depending on whether this is press fit or not, I mean, obviously the resistance properties will be affected going through this, but it will also carry it, and the power pin will be in place as well. So it will replace the missing copper to a certain extent, I guess.
Good. Yeah.
You need a fulfilled.
You can 3D print copper these days.
Well, including the pin, including the socket.
Yeah, no, those would be almost perfect on the inside. So
Yeah.
you'd need to have a bushing.
Well, you need the beryllium spring in the middle as well for the making.
Yeah.
Okay. So I think that so in your analysis, I don't know if you drew any conclusions. I was sort of encouraged that we weren't a million miles off. If with your 200 amp, where you sort of overspec'd it to 200, when the total load I think was in the order of 105 or 110 amps at worst case, if it was a fully loaded, like a kilowatt per module plus like 500 watts for the each CPU, and then a 10% overhead for efficiency losses elsewhere, then I think I ended up with like a total of 110 amps. And what we've got to remember here as well is obviously, as we roll down this bus bar, we're going to be disconnecting from the your two loads are tapped off right at the beginning, so your current almost halves as soon as you've gone past these two loads. So as we go down this bus bar. The only other thing to note is you can see it. This is a OCP industry standard connector. We'd need probably a modified connector here to mate efficiently with these bus bars. So I mean, this is literally just stuck on there at the moment. But you can see these.
Probably the way to go is the way that this particular part is made with these threaded studs here, is there would be a very short piece of cable of comparable size that would jump over and screw down to the top surface of this. It looks like, you know, a 3-inch wire or something short.
Right. You wouldn't. It wouldn't be a modified connector design. That would be too difficult to do, I guess.
Yeah, you don't want to do that.
Right. Anyway, I guess there are different versions of this I have seen. So
yes, there's a dozen.
Right. So we would need to pick the best one for this setup.
Yeah, but I think what you've done here is perfect.
Okay.
You know, whatever, that's an easy fix.
Okay. All right. Good. Okay. So
but I can't run the thermoelectric ANSYS here, where you could build the 3 bus bars, load it up on the left and right, draw out on each of these spots here. But there's a regular thermoelectric heat analysis would tell this story very well and size the bus bar to whatever you can tolerate for temperature rise on the copper.
Yeah, okay. And by the way, I do think I've got a little bit of room. So this is the aluminum frame, and there's a rubber seal goes around. So I think we can, well, I think we can make this wider, slightly wider, this middle one, and I think we can make it slightly thicker as well. But again, it's marrying up with the challenges of routing cables everywhere as well. So like there's a channel for routing cables here when I was working with the 30 gauge, and so if we can go to like 34 gauge, then that dramatically improves. We can actually bring cables across everything. So that really does help out there. So I think we can bolster up these copper bars to get to where you were, you know, where you were saying it should go, Howard.
Yeah.
So I'm relatively relaxed about that. I know we're just over time, so I'll let everybody go. But just for those of you that don't know, in fact, I've not shown the water. Let me put the water connector on. So basically, the idea is this exoskeleton frame will mate up with the blind mate of the ORV3 rack that we can bring the water in. And I'm talking to Cool IT about this. I was hoping, unfortunately, they couldn't join today. But we would bring the water in. So this would mate with the blind mate of the chassis. This would be like a manifold built into this frame, and you have little holes where you can connect the rubber pipes to go to the individual water cooled or liquid cooled plates that go on the processors, and there's ones out the front as well that would go over the CPU ones. So this is the exoskeleton frame that we're looking to build. By the way, Howard, is this something that Lotus would take on as a whole piece, or you would just be interested in a bus bar piece? You know, do you do water manifolds, or is a company, or?
I have no idea. Somebody else can answer that question.
Yeah, I guess we need a partnership. So on the assumption we need to work with a cooling specialist like Cool IT and a bus bar specialist, and let's say sounds like you're a bus bar specialist, then we need to jointly design this frame ideally. And so how do we bring those two worlds together of the suppliers of bus bars and water cooling stuff into this frame design? Okay. All right. We've run over by a few minutes, so I'll call it a day, but thank you for everybody that's joined. There was a couple of other people joined, wasn't there? Kevin Cameron joined, and also Mitch Wright. So I'll add them to the list. All right, guys. On that note, thank you very much. Good discussion today.
Thank you all. Bye.
Thank you.
Thank
Bye.
you.
Bye.
Bye.
Alan, enjoy your day at the beach.
Thanks.
Nice
Bye.
background.
Yeah, I need to update that one. Cheers. Bye.